record. Okay. Check. Okay, I checked the chat, so everybody in the chat I think is good. So, sorry, this always takes a fair amount of time. Okay, I think we're in business. I'm changing the assignment a little bit in 6.4. And I'll probably start some of 6.4 today. 6.4, throw out 19, skip 19, but put in 23, please. Okay. So trade you 19 for 23. As the semester goes on, there might be more, again, because I'm switching between the 7th and 8th edition. Sometimes they're the same, sometimes they're not. All right, everybody got that? Throw out 19, put in 23. All right, and calendar-wise, so I'm going to finish 6.3 and start 6.4. I think we'll be able to do that. And after the break, I'll lecture a little bit more, and then I'll put you in your breakout groups for the next quiz. Okay. All right, and we're aiming for Tuesday, September the 8th for the first exam. Again, I'm aiming for the second half of class. So the first half, I'll do more new stuff. I'll stop and let you ask questions, and we'll take the test after the break. Okay, and again, you can have a formula sheet, one cheat sheet like this piece of paper, front and back, 8.5 by 11. And you can put any formulas that you wish, and you can use a calculator. All right. Okay, so here we go. So I'm going to start you off with 6.3, number 11. Okay, so it was y equals x to the 3 halves, bounded by y equals 8, and x equals 0, and you're spinning it about the x-axis. Okay, you can ignore that. That's just the final answer that I wanted to make sure I had it with me. Okay, so y equals x to the 3 halves looks something like that. I mean, if you stop and think about it, y equals x squared has that general shape, and y equals x goes like that. So it's still curved up, although it's not as important. Okay, y equals 8 is a horizontal line. X equals 0 is the y-axis. So we're taking this region and spinning it about the x-axis like so. All right, so if we're doing the shell method, which we are, then our slices are going to be delta y. So here's a delta y. It'll change in y. So I'm integrating with respect to y. Now, if I integrate with respect to y, I need to solve for x. X is a function of y. So how do I get rid of that 3 over 2? Yeah, you would say something about 2/3. You don't really say multiply by 2/3. That would be if it's down here. But I know you want the 2/3 up there. So the trick is to raise both sides to the 2/3 power. So see here where I got y equals x to the 3 halves? Then you raise as an exponent to the 2/3. So the 2/3 is floating up here at the same level as the 3 over 2. Okay, so you raise as an exponent to the 2/3. That way the 3 halves and the 2/3 cancel out. So you have x equals y to the 2/3 power. So there we go. X equals y to the 2/3. Okay, so I take this very thin rectangle, spin it about the x-axis. You're not seeing discs or shells. You end up with cylinders, cylindrical shells. Okay, the tin part of the can, as it were. So imagine a can of corn, no top, no bottom. We're trying to talk about the volume of just that can. Spin that around, that's what I got. Okay, and don't forget there's actually more slices. You did a lot of this maybe in Calc 1. Another slice here, another slice, another slice. This is just a so-called typical slice. You let the number of slices approach infinity, delta y approaches 0, you get the integral. Okay, so we know we're integrating 2 pi rh. The height, distance from here to here, is x. And the radius, the thing here that I spin around, the radius is y. Okay, so always go back to this fundamental picture for when you first learn the xy coordinate system, right? I'll make it in the first quadrant just because it's easier. But you had a point x comma y, right? Like 6 comma 4. Okay, this distance right here is x, right? And this distance is y. So that corresponds to what happens over here. This distance is x. It's from any point to the y-axis. Again, you could argue, well, this point and this point are not quite the same, which is true, but for continuous functions, it doesn't get a chance to change that much, or in the limit. We say in the limit, as delta y approaches 0, they're practically the same. Okay? And similarly, distance from any point of this rectangular region to the x-axis, that's y, because it corresponds to this picture. And again, yes, you might say a point on the lower part doesn't quite match a point on the upper part, but if delta y approaches 0, we can treat them as the same. Okay, in a nutshell, yes, we are integrating 2 pi xy, because the radius is y and the height is x. All right, so I'm going to integrate with respect to y, so I'm going from 0 to 8. So integral from 0 to 8, 2 pi x, here's x. Okay, maybe I'll emphasize that by writing that here. 2 pi x y dy. Circumference times the height. In this case, 2 pi xy. So 2 pi xy. All right, so 2 pi comes outside. Y to the 2/3 times y to the 3/3, right? You can pretend there's a 3 over 3. So I have y to the 5/3 now. So I'm integrating 2 pi, integral from 0 to 8 of y to the 5/3 dy. Okay, so power rule, add 1. 1 more than 5 over 3 is 8 over 3, right? 5/3 plus 1, 5/3 plus 3/3 is 8/3. Divided by 8/3, there it is, right? And again, I'll use this shortcut in general from now on. If you divide by 8/3, it's the same as multiplying by 3/8. And you're going from 0 to 8. Okay, a little bit of cancellation here. That's like pi over 4, right? That 2 cancels at 8. So pi over 4 times 3. 8 to the 8/3 minus 0 to the 8/3, but 0 to the 8/3 is just 0. We like plugging in 0. Okay, so pi over 4 times 3. 8 to the 8/3. You might recall this means you want the cube root. So cube root of 8, 2. And then you raise it to the 8th power. 2 to the 8th power, you can punch in your calculator, comes out to be 256. And clean this all up, answer comes out to be 192 pi. So my final answer is 192 pi. Okay, again, geometrically, what is that? That's what you get when you take this funny shape, okay, this region here, and spin it about the x-axis. Okay, so we're doing the so-called shell method now, S-H-E-L-L, and we get 192 pi. Okay. Okay, next one I was going to show you was 15. We did something like it, but I might as well give you the exact one. And this one's a little tricky because you're not spinning it about the x or y axis, but somewhere else. Okay. All right, so we have y equals x cubed, y equals 8, x equals 0, spin it about x equals 3. And this is the final answer. I just wanted to have it ready, but okay, x cubed, I know looks like that. And yes, there's another piece over here, but we're not worried about that. X equals 0 means the y-axis. and y equals 8 is up here. So the picture is almost like the other one, somewhat similar, but it looks like this. And we're asked to spin it about x equals 3, so way over here. Okay, so this time my slice is going to be delta x. Okay, I don't want to go delta y. If I slice with delta y, can you see it'd be kind of like a washer method? And they told me not to, so I'm going to be doing the shell method. So there's a couple of things different about this one. Okay, so we know integrating 2 pi r h, or circumference times the height. Okay, so here's my cross-sectional slice, delta x. So what is this height? Well, it's the upper minus the lower. So the height is 8 minus x cubed. The upper function is 8, the lower function is x cubed. So the height is a difference between the two, 8 minus x cubed. And now the radius. So if I take this thing, spin it way over here, spin it about x equals 3, then the distance from here to here, that's going to be my radius. So how am I going to figure that out? Okay, well, how far is it from here to here? 3, right? From this vertical line to this vertical line is 3. How far is it from a point on this rectangle to the y-axis? That's x. That looks like this picture. Can't quite show you both at the same time. But again, if you take any point in the first quadrant, go back over here to the y-axis, that's x. Okay, so this distance right here in green is x. So if this is 3, this is x, then this must be the difference, 3 minus x. So the radius is 3 minus x. Right. That was more than half the battle right there to figure out what's the radius and what's the height. Okay, so one more time. For the shell method, we integrate 2 pi rh. Okay, the height here, see, this doesn't come all the way down to the x-axis. It stops here. So what's the height? It's the difference between this and this. In other words, 8 minus x cubed. And we had to figure out the radius. So if I take this rectangular region, spin it way over here, this would be my radius from here to here. So I figured this was 3, this is x, so the difference is 3 minus x. So there we go. So now I integrate 2 pi rh. Okay, x is going from 0 to 2. So the volume is 2 pi, you can factor out to 2 pi. 2 pi integral from 0 to 2 of r, which I now know to be 3 minus x, times the height, which I now know is 8 minus x cubed, times the dx. So there we go. Okay, multiply all this stuff out, FOIL it out. So 3 times 8, 24. 2 pi's in front. 3 times negative x cubed, negative x times 8, and negative x times negative x cubed is x to the 4th. So that's what I have. Okay, and unfortunately I reached the bottom of my paper, so I got to go back up, but I'll go one by one. So 2 pi. What's the integral of 24 dx? 24x. What's the integral of negative 3x cubed? It's negative 3x to the 4th over 4. What's the integral of negative 8x? Remember, you can pretend there's a 1 there. So negative 8x to the 1, that would be negative 8x squared over 2. Negative 8x squared over 2 is negative 4x squared. And how do you integrate x to the 4th? X to the 5th over 5 from 0 to 2. 2 pi. Parentheses, plug in 2. Parentheses, plug in 0. I like plugging in 0. Put a 0 there, that's 0. Put a 0 there, that's 0. That's 0. It's all 0. Right? 2 maybe not that easy. let's see, 24 times 2 is 48. Put a 2 there. 2 to the 4th power, 2 times 2 times 2 times 2 is 16. So negative 3 times 16 over 4. Put a 2 there. 2 squared is 4. So negative 4 times 4 is negative 16. And put a 2 there. 2 to the 5th power, 2 times 2 times 2 times 2 times 2 is 32. You can use your calculator. And so I get 32 over 5. Okay, a little bit of cleanup. Let's see. This comes out to be a nice number, negative 12. So negative 3 times 16 over 4. 16 divided by 4 is 4. So it's 3 times 4 is 12. So I have this. And then I combine 48 minus 12 minus 16. That's a 16 there. Is 20. See, 48 minus 12 is 36. 36 minus 16 is 20. So 20 plus 32 over 5. Then I get a common denominator. Fortunately, this is 20. Well, 20 is 100 over 5, right? If I go like this, multiply that by 5, multiply that by 5. 20 times 5 is 100. And what's 100 plus 32? Well, 132. So 132 over 5 times 2 pi. Final answer is 264 pi over 5, like that. Okay. All right, again, notice these problems are right off the homework. Okay. So even though I say there's a 70% requirement for doing the homework, you really don't have to do that much because you've seen already, I've done a whole bunch of these already anyway, right? So you just have to finish the rest of them. Okay, so that's that one. All right, so I'm done with that portion. The next set of problems is a little bit different. So 37 through 41. The region bounded by the given curves is rotated about the specific axis. Find the volume by any method, which means you can pick either the disk or the shell method. And to be honest with you, that actually makes the problem harder. Okay, because if it says do the disk method, okay, they told me to do it, I'm doing it. And if it says do the shell method, you know what to do. But if it says you can pick any method, that's actually a disadvantage, right? Because then you have to decide for yourself, do I want to do the disk method or the shell method? And by the way, I just mentioned on the exam, if I say do it by the disk method or washer method or the shell method, you must do that technique. But if I say solve by any method, you can pick either. But frankly, sometimes that makes it harder for students, right? Because then you have to say to yourself, oh, do I want to do the disk method or do I want to do the shell method? But if I say do the disk or do the shell, you don't have to worry about it. You know it's going to work, right, if I do whatever is specified there. Okay, so I'll show you a couple of these. And you have to pick which is the right way. Okay, now I showed this to you yesterday, but a quick summary. Okay, and again, if you want to put this on your cheat sheet, you may. So for the disk method, you're essentially integrating pi r squared. Quite often it's pi x squared or pi y squared. And for the washer method, it's really the same as a disk method, except there's a hole in the middle. Right? It's the whole idea of a washer. A cross section would look like this, right? Where you have a bigger radius and you have a smaller radius. So big R and a little r. So you're going to be integrating pi big R squared, like from here to here, big R, minus pi little r squared. Then, of course, you have to decide what's the big R and what's the little r. And then the shell method, you're basically integrating 2 pi RH, or you can think of it as circumference. Formula for circumference is 2 pi r times the height. Is that right? All right, so I was going to show you 37. So jump over here to 37. Y equals this thing, negative x squared plus 6x minus 8, bounded by y equals 0, and you spin it about the y-axis. Okay, so let's pretend you don't know the graph yet. I'll show it to you in a second. But one thing you should know, do you recall what's the graph? If I have something like that, negative x squared plus 6x minus 8. Okay. It's a quadratic, so it's a parabola. So I know it's a parabola. And which way does it open, up or down? Hint, look over here. There's a minus sign. That means it's going to open down. Okay, so I know it's going to look like that. I don't know it's that specific yet. I'll get to specifics, but I know it's opening down. Now, how do I know it's exactly like that? Okay, it's bounded by y equals 0, which is the x-axis. Okay, so I need to know where I'm integrating from. Am I integrating from 1 to 5 or 3 to 10 or whatever? Okay, so I have to find out where it touches the x-axis. So I set this equal to 0. So 0 equals negative x squared plus 6x minus 8. That is a quadratic equation, okay? But I don't like to have a negative in front. Simple remedy, multiply both sides by negative 1. Okay. Usually it's a good idea when you're solving quadratic equations to have the a, the number in front of the x squared, to be positive. I mean, you can do it if it's a negative, but it's usually easier to have it positive. So quick remedy, multiply both sides by negative 1. Negative 1 times 0 is 0. Negative 1 times all of these just changes every sign, right? So that becomes positive x squared minus 6x plus 8. And that looks factorable, right? A minus and a plus means they're both minuses. Okay, so what two numbers have a sum of 6 and a product of 8? That's 4 and 2, or 2 and 4. So factors into 0 equals x minus 2, x minus 4. So that gives me 2 and 4. So 2 and 4. And I know the parabola opens down, so I'll just quickly go like that. Okay. Or you could plug in 3, you know, a number in the middle. If you plug in 3, this will be a positive quantity. Take my word for it, but it'll work. Okay, so I'm taking this region and I'm spinning it way over here. I'm not spinning it this way. Okay. In fact, let's see, if I spin it this way, can you kind of see what you have? It's almost like a football. Can you see if I turn that around, you get something that looks like a football? American football, not soccer ball, but American football that kind of looks like that. But anyway, we're going this way. And what does it look like? I don't know. It's sometimes hard to visualize, but I'm going this way. Now, I don't want to slice this way because then I'd have to solve x as a function of y. They already gave me y as a function of x. So if I slice delta x and then spin it this way, do I see a disk or do I see a shell? Okay, it looks like a shell, right? If I take this thing, spin it way over here, I get a shell, which really means it's like a cylinder, hollowed out can of corn, where you don't have a top, you don't have a bottom, and you're only considering the metal part, very thin. And there's another slice here, and another slice here, and another slice here, and another slice here. So chop, 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 chop this up into millions of pieces that n approach infinity, that delta x equals 0, we get the integral. Okay, what's the height? Well, the height is y, which is negative x squared plus 6x minus 8. And what's the radius? Well, the radius is going from here to here, and that's x, because that, once again, looks like the picture where you're going from a point back to the y-axis. So again, I am going to integrate with the shell method 2 pi xy. So here we go. The volume is the integral from 2 to 4. So this time it's not going to be as nice. Okay, I don't get to plug in my favorite number 0 or my second favorite number 1. So unfortunately, I have to integrate from 2 to 4. 2 pi x y, but what's y? Negative x squared plus 6x minus 8. So negative x squared plus 6x minus 8 dx. Okay, so 2 pi x y. But I don't write the letter y. Since I'm integrating with respect to x, I have to change y to what it's equal to. Y was equal to this stuff. Okay, and there we go. So factor out the 2 pi. 2 pi comes out. Distribute. So negative x cubed plus 6x squared minus 8x. And that's what I'm going to integrate. Okay, so 2 pi, here we go. negative x cubed, negative x to the fourth over 4, 6x squared, 6x cubed over 3, 6x cubed over 3, 2x cubed. Negative 8x, that's like negative 8x to the 1. So negative 8x squared over 2. Negative 8x squared over 2, negative 4x squared. And from 2 to 4. So leave the 2 pi alone. Plug in 4. Plug in 2. So plug in 4. It's negative 4 times 4 times 4 times 4 divided by 4. You can punch it in your calculator. Comes out to be negative 64. Or you could say one of those 4s cancels this 4, so you have negative 4 cubed, which is negative 64. Okay, plug in 4. 4 cubed, 4 times 4 times 4 is 64. Times 2 is 128. And put a 4 right here. 4 squared is 16. 16 times 4 is 64, so negative 64. I'm going to plug in 2, but I noticed ahead of time, this is all 0. Right? 128 minus 64 minus another 64 is 0. That's nice, so that's nothing. Minus, okay, now I plug in 2. So 2 goes there. 2 to the 4th power. 2 times 2 times 2 times 2, 16. 16 divided by 4 is 4. And there's a negative in front of the whole thing, right? So negative 4. Plug in 2 here. 2 cubed is 8. 8 times 2 is 16. Plug in 2 here. 2 squared is 4. 4 times negative 4 is negative 16. So I have 16 minus 16. That's nice. So these drop out. So that's nothing. These 2 are nothing. So I have negative negative 4, which is a positive 4. So I have 2 pi times 4. Final answer is 8 pi. So I have 8 pi as my answer. Okay. Okay, and then just one more I want to do, and then I'm done with the section, and I can get started with 6.4, which is on work, W-O-R-K, the physics idea of work. Okay, so 41, please. So 41, ignore this. I totally goofed here, so just ignore this completely. Sorry about that. X squared plus parentheses y minus 1 squared equals 1. Spin it about the y-axis. Okay, so if you recall from your early work, this is a circle. The center is 0, 1. Okay, so you might recall if you have something called x minus h squared, the center is h, comma, and then if this were, say, y minus a k squared, okay, the y coordinate of the center is k. Okay, so the center is 0, 1. You change the sign of this. So the center is 0, 1. The radius is the square root of this number. Square root of 1 is 1. Okay, so ignore this. The center is 0, 1, and the radius is 1. So it looks like this. I have 0, 1, right? And I go 1 up, 1 down, 1 left, 1 right, and it goes like this. Okay, I spin it about the y-axis. If I spin it about the y-axis, okay, if I take this circle and spin it about the y-axis, can you see what I would end up with? You end up with a sphere. Yes. And this was actually a reason for that. You don't really need this. Okay. Now, if you have this whole circle, spin it about the y-axis, you get the sphere. But if you stop and think about it, if you only had half the circle, a hemisphere, if you just take this and spin it around the y-axis, you still generate the entire sphere, don't you? Okay, so the way it is set up, it looks like it's easier to do the disk method this time. If I slice delta x, I'd have to figure out the top and the bottom, so I'd have to do some weird, y equals something and y equals something. That's too much work. So it looks like if I go like this, if I slice delta y, spin it this way, I see the disk, right? So if you take this and spin it around, can you see the disk? You end up with a very, very thin disk, almost like a coin, not very high at all. But it does require me to solve for x. I need x as a function of y. Okay, so back up here, how do I solve for x? Right? So first I'll subtract that over. So subtract y minus 1 squared. It looks like this. How do you get rid of the square? Square root. So x is the square root of all this. Say, what about the plus or minus? Okay, if you have the plus part, you have the part on the right side. If you want the negative, it would be the left side. Okay. Now, what do we want? We want the right side. You actually could do the problem with the left side, in which case you have a negative here, but who wants to have a negative when you don't have to, right? So x is equal to this. Okay. It's worth it to clean it up. So what is y minus 1 squared? Y minus 1 squared is this, y squared minus 2y plus 1. Right? That's like parentheses a minus b squared, a squared minus 2ab plus b squared. So 1 minus parentheses y minus 1 squared. Okay, distribute. Okay, do you agree the 1 cancels this negative 1 right here? It's going to be 1 minus 1. So there's no constant. These two cancel out. Right, we're distributing. So I have negative y squared plus 2y. Negative y squared minus a minus 2y, which I choose to write this way. So radical 2y minus y squared. All right, so I'm ready. That turns out to be the radius. Okay, so if I take this piece, spin it about the y-axis, this is the radius. And the radius is just x. And what is x? I now found it to be this, radical 2y minus y squared. Okay. All right, so we're doing the disk method. So do you recall for the disk method, what do we integrate? We integrate pi r squared. So here it is, integral from 0 to 2, 0 to 2 of pi x squared. But I don't leave it as x. I have to have the letter y because I'm integrating with respect to y. Right? My slices are delta y. Delta y in the limit is dy. So radical 2y minus y squared is x. So pi r squared is pi x squared. But what's x? This thing. So radical 2y minus y squared squared. That's nice. What happens when you have a square root and you square it? Just take off the square root in the 2. Take out the pi. 2y minus y squared. Okay, so what's the integral of 2y? 2y squared over 2. 2's cancel out, so y squared. Integral of negative y squared, negative y cubed over 3. And by the way, a side note, how can you check any integration? Differentiate, right? Let's check. What's the derivative of y squared? 2y. What's the derivative of this thing? Well, if you bring the 3 down, right, the 3 will come down, knock out that 3, and then you have y squared. So it works. Okay, from 0 to 2, I like 0, right? Parentheses, plug in 2, parentheses, plug in 0. But 0 squared is 0, 0 cubed is 0, divided by 3 is 0, 0 minus 0 is 0. Okay, quick word, don't get too sloppy and assume, oh, every time I see 0, it's automatically 0. Well, be a little bit careful. Like if you see e to the 0, right? If you see e to the 0, that's not 0. E to the 0 is 1. And also maybe be careful when you have trig functions, right? Now, if you have a sine function, yes, the sine of 0 is 0, but not the cosine of 0. Right? Do you recall what's the cosine of 0? Cosine of 0 is 1. Right? So a little bit of caution. So maybe I should say, if you plug in 0, there's a good chance, maybe I'll say, there's a good chance it's 0, but double check to make sure it is 0. So I put a 0 here, yeah, that's 0, and yeah, that's 0, so it is that. So I just plug in 2. 2 squared is 4, 2 cubed is 8, 8 over 3. So 4 minus 8 over 3. 4 is 12 over 3. So 12 over 3 minus 8 over 3. Final answer is 4 pi over 3. And that's it. Okay, so that's as much as I was going to show you from 6.3. So I'm done with 6.3. I'm going to start 6.4. So we have 6.4 and 6.5 left for the test a week from Tuesday. Okay, and I'll get started with some of this right now. Again, you're supposed to turn in at least 70% of the homework, but hey, I've done what? Half, more than half in some cases. Okay, so 6.4. So let me start 6.4. The concept is work, W-O-R-K, the mathematical or the physics idea of work. That's on page 455, I guess. Okay. All right. So basic idea from physics. I know some of you are taking physics, or maybe you had physics in high school. Okay. Work is equal to force times distance. Some of you already know that. If you've never heard of that before, you can put it down or put it in a cheat sheet. Work is force times distance. So the physics definition of work is force times distance. So don't think of it as the regular work, like I go to work or I'm doing my job. I'm working. Like for me, I'm working right now. No, the different definition of work in the physics sense is force times distance. Okay. All right. And let's see. For the benefit of those of you that don't have the text, I'll try to show that for you, although it may not come out that good. Okay, let's see. We had to go up to what problem? 23, it looks like. So let me see if I can show that to you. So this is page number 458. So there's the bottom there. Sorry, that's the best I can do. Okay, and then over here, let's see. There's 5 down to about 19-ish, I guess. I'll try to move the angle a little bit. Or it might, well, that might be a little bit better for some of them. Okay, I'll go like that. Okay, then 19. Show you that. And then the very bottom. Let's see, 23 was the last one. Yeah, there's 23. So it's there. Let me try to change the angle again. So if you look back at the video, maybe certain angles are better than others. Okay, so there we go with that. Okay, so some more introduction to work, 6.4. Okay, so work equals force times distance. And we have to get used to some units. Okay, now in the book, they give us some in the metric system, and they give us some in the English system. Okay, so in metric, work equals force times distance. Okay, the unit of force is the Newton. We write N, Newton, N-E-W-T-O-N, named after Sir Isaac Newton. Some of you have heard of Sir Isaac Newton, a mathematician and physicist and so on. Distance is measured in meters, M. Okay, so force is newtons, M is meters. Okay, multiply them together, force times distance. You have something called a Newton meter, and a Newton meter is called a joule, J-O-U-L-E. Okay, so we use J for joule. I know some of you have heard of this, some of you haven't. Okay, Joule is a famous physicist also, James Prescott Joule. So to honor Joule, we use the J. Okay, so J is a joule, it's a unit of work, is Newton times meters. Okay, now in the English system, for force, we say pounds. And of course, we're all used to the concept of pounds. Like something weighs 5 pounds or 100 pounds or whatever. Distance is feet. Multiply them together, it's called foot pounds. That's literally what it's called. We have no other names for it. It's called a foot pound. All right. If you hear a whirring noise on my end, that's coming from my computer. Sorry about that. My computer is dying. I'm supposed to get a new one tomorrow, so I just hope it lasts until the end of today. And then hopefully the new computer is better. But if you hear a whirring, that's what it is. Sorry about that. Okay, so work equals force times distance. So problem number 1. Okay, it says a 360-pound gorilla climbs a tree to a height of 20 feet. Find the work done if the gorilla reaches the height in 10 seconds and 5 seconds. Okay, so this is obviously English system. We have feet in pounds. So 360 pounds going 20 feet. So I just multiply them. So just punch out 360 times 20, and you get a certain number of foot-pounds. So what is 360 times 20? 7,200. So I'm not sure you can see this. 7,200 foot-pounds. So the answer is 7,200 foot-pounds. And actually, the problem's a little deceiving. They say 10 seconds, 5 seconds. It doesn't matter. Okay, work is force times distance. There's no time involved at all. So it doesn't matter if it's 10 seconds, 5 seconds, or 50 years, or whatever. Okay, it's the same amount of work. Work is not dependent on time. Okay, so you just multiply the force times the distance. That's it. Okay, and frankly, that was a very simplistic problem. So you're probably not going to get a question like that on a test. Okay, that's frankly too easy. Okay, force times distance. So what makes the problem harder? Well, here you have a constant force and a constant distance. You don't really need calculus for this. You do need calculus for other problems because maybe in the next problem, you do not have a constant force, or maybe you don't have a constant distance, you see. So that makes it a little bit different. Okay, good example of that would be something like number 3. So let's look at number 3. If you can't read it, don't worry. When I show you the paper, hopefully it's more clear. A variable force of 5x to the negative 2, if you can't read that, that's 5x to the negative 2 pounds, moves an object along a straight line when it is x feet from the origin. Calculate the work done in moving the object from x equals 1 foot to x equals 10 feet. Okay, so you have a variable force, 5x to the negative 2 pounds. You're starting from 1 foot and you're moving to 10 feet. Okay, so let me move the text and show you what's going on. Okay, so here's the force function. F is equal to 5x to the negative 2, which is the same as 5 over x squared. You're starting here at x equals 1. You're moving it to x equals 10. But unlike the previous problem, unlike the gorilla problem, it's a different force as I go along. For instance, plug in 1. What do you get when you plug in 1? 5. So right here, I have to push. Imagine pushing this with 5 pounds of force. But by the time I reach 10, what do you get when you plug in 10? Well, 5 over 10 squared, that's 5 over 100, 1/20th. So over here, you don't have to push it very hard at all, right? So you don't push with the same force at the beginning as at the end. And I guess the idea is that you have to have more force at the beginning, but as you go further down the line, you have to use less and less force. Okay, so it's not like the gorilla problem. And you'll hear me say the gorilla problem a lot. That's a constant force, a constant distance. Okay, here you do not have the same force. Okay, so that's the difference here. So you say, how do I work that out? So here's the concept. Okay, suppose I chop this up in a whole bunch of tiny little pieces. We always do that in calculus. Here's a typical piece. So chop, 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 chop. You know, millions and millions of pieces. And here's a typical delta x. Okay, so here's some slice. And here's that concept. If delta x is really, really small, 0.0000001. Okay, now this is somewhere in the middle. So let's pretend this is 5. Okay, the left side is 5. The right side is 5.00001. Right? There isn't much of a difference between 5 and 5.0001. So if I plug in here, I'm pretty much going to have the same thing, right? So it doesn't really matter much if I plug in 5 or 5.0001. It's the same thing. And you can make the approximation better and better and better if delta x approaches 0. Like 5 and 5.0001, right? They're very, very close. So if I take this slice right here, and if delta x is very small, I'm moving that slice the same distance, which means I claim for a very, 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 very thin delta x, it is the gorilla problem. It's a constant force. Yeah, we know it's not really the same, but if delta x is really small, it doesn't matter if I pick the left endpoint or the right endpoint. This is practically the same. And I'm moving the same distance. Yes, I'm not quite, the distance from here to here is not quite the same as here to here. But if delta x is really, really small, we can approximate that. And the approximation becomes quote unquote perfect in the limit as delta x approaches 0. So for this tiny little slice, it is the gorilla problem. So I'm going to write it like this. Delta W, my change in work. So delta is change. The triangle is a Greek letter delta. Delta for change, C-H-A-N-G-E, change. My little change in work is the force, 5 over x squared, times the distance, delta x. Same for the first slice, second slice, third slice, all the way down the line. The concept is, yes, n approaches infinity, the number of slices approaches infinity, delta x approaches 0, you basically integrate. Okay. Now I gave you a lot of verbiage there, but essentially what's happening is you just integrate the force function. Okay. So if you say to yourself, I didn't understand any of what you said here, okay, what do I do? Just integrate the force. So you just integrate 5x to the negative 2 dx, and that'll be your answer. Okay. So I'm supposed to show you the theory, but if you can get the theory, just integrate the force function from 1 to 10. So there we go. And what happens at delta x? In the limit, it becomes dx, which means you can just drop it, per se. Okay, so integrate x to the negative 2, power root, x to the negative 1 over negative 1, right? From 1 to 10. This is like negative 5, 5 over negative 1. X to the minus 1 means 1 over x. Okay, you can leave out the negative 5, factor out the negative 5. Plug in 10, 1/10. Plug in 1, 1 over 1 is 1. So I have negative 5 times 1/10 minus 1. 1/10 minus 10/10 is negative 9/10. So negative 5 times negative 9/10 is a positive 45 over 10, or 4.5 foot-pounds. So my answer is 4.5 foot-pounds right here. Okay. And so again, just quick and dirty. If you just want to know what to do, what do I need to know for the test? For this function, just integrate the force function from 1 to 10. Okay. All right. So I'll do maybe one more and then perhaps we'll break after a while. Okay, so some other things we'll need. So again, ignore the date. So we have work equals force times distance. We are going to need this a little bit later. And some of you physics people know this. Force equals mass times acceleration, or F equals ma. Okay? Sometimes called Newton's second law of physics, second law of motion. F equals ma. Force equals mass times acceleration. Now, in the problems that they give us, we only have to worry about that in the metric system. You don't have to worry about it in the English system. But let me give you units. Okay, force is newtons, just like before. The basic unit of mass that we're going to use here is the kilogram. Kilogram is 1,000 grams, so kilograms. And acceleration is going to be meters per second squared. Meters per second squared, not meters per second. Meters per second is velocity, but meters per second squared is acceleration. Okay, so quite often we're going to find the weight, okay, and the weight is a force, okay, and we're making assumption, if we don't say otherwise, we're on Earth, okay, we're all on Earth right now. I mean, you can do these formulas on the moon or on Mars or something like that, but let's assume we're always on Earth for these problems, okay. All right, in the English system, just to let you know, you'd have pounds, and then you need something for weight. It happens to be called the slug. Now, you don't have to write that down if you don't want to, because we don't have any homework problems involving it. But for those of you that want to know, and maybe you get this in your physics class, the slug is a unit of mass in the English system. Okay, I just put that extra. You don't really need to write it down. You don't need to know it. I'm never going to give you any problems that involve the slug. But in case you want to know, the slug is a unit of mass in the English system. Okay, sometimes we need to use G. G is called the acceleration due to gravity on Earth. Okay, on Earth, the acceleration due to gravity is 9.8 meters per second squared, or 32 feet per second squared. Okay, now we're almost never going to use this for our class, but 9.8 meters per second squared, you can put that down on your cheat sheet. I know some of you physics people already have that memorized maybe. Okay, this is the acceleration due to gravity on Earth, 9.8 meters per second squared. Now, if you're in a different heavenly body, they have their own acceleration due to gravity. For instance, if you're on the moon has a smaller acceleration due to gravity, right? So maybe if you've seen footage of the astronauts from Apollo on the moon, right? And they drop something or they walk up and down, it's not quite the same as Earth, or they can jump higher, or they throw an object up in the air, it takes longer to come down, right? Because it's a little bit smaller acceleration due to gravity. And likewise, same thing on Mars. Okay, there are rovers on Mars now, perhaps. The acceleration due to gravity is smaller also on Mars. Okay, so every heavenly body would have their own acceleration due to gravity, but on Earth, it's 9.8 meters per second squared. And of course, if you're floating out in space, like if you're on the International Space Station, let's say, then the acceleration due to gravity is 0, right? Because then, for instance, you might have seen some astronauts in the space station, they would take this pen. Now, if I drop my pen, it'll just go like that. But if you're in an International Space Station and you drop it, so to speak, it'll just float because the acceleration due to gravity is 0 there, right? Okay, but on Earth, we use 9.8 meters per second squared. Okay, so we need to use all these things for doing some of the problems. Okay, so I'll show you number 9, but I probably won't do it until after the break. Okay, so for number 9, just give you a heads up. Okay, 2 joules of work. Okay, so that looks like we're in the metric system, is needed to stretch a spring from its natural length of 30 centimeters to a length of 42 centimeters. Okay, first thing is I see centimeters, but the understanding for metric system is that we're in meters. So I have to change these to meters. Now, there are 100 centimeters in a meter. So that's going to be 0.3 meters, right? And that's 0.42 meters. Okay, how much work is needed to stretch the spring from 35 centimeters to 40 centimeters? That's going to be 0.35 to 0.40, right? In meters. And how far beyond the natural length of the force of 30 newtons keep the spring stretched? Okay, so I have to show you another formula in order to do that, and then we'll break. Okay, we have something called Hooke's law, top of 457. Hooke's law. Again, some of you physics people have heard of that. If you've never heard of it, put it down on your cheat sheet. Okay, it says that F is equal to Kx, and some of you physics people may have heard that. Force is equal to a constant times x. Okay, so it turns out for a spring, like here's a picture of a spring, right? There's something called a natural position of a spring. So if you have a spring and you have something attached to it, there's a place where the spring likes to be, a place where it's quote unquote happy, okay? And we call that 0, okay? And if you wanted to go either this way or this way, you have to either push it this way or stretch it out that way, okay? So you have to apply a force, and it turns out the force that you need is dependent on how far you are, okay? The further away from the home position that you are, the more force that you have, right? So to move this maybe just 1 centimeter, you don't need that much. But if you want to move it way out to here, it's almost as if the spring says, no, I don't want to do that, right? There's more resistance in doing that. And likewise, if you want to shove it in, right? If I'm going to shove this thing to the wall, if I just want to shove it, a millimeter, you don't have to push it that much. But if you want to push it, scrunch it up way up there, you're going to feel more resistance. It's almost like the spring is saying, no, I don't want to do that, right? I resist that. So the force function is Kx. So just mark down force equals Kx, and we will stop right there for now. Okay, so we will break. Let's see, what time do we have right now? Almost 8:10. Okay, let's start up again at around 8:20-ish. Okay, so 8:20, I'll lecture a little while, and then I'll give you folks the quiz after that. Okay, so break time. I will stop the share and pause. Okay, we're back. So let me try to summarize what happened. So they told us we have 2 joules, which is 2 Newton meters. And I've got a little picture here of a spring. Okay, the natural position for the spring, they said, was 30 centimeters. 30 centimeters, but I need to change that to meters. So that's 0.3 meters. And then we're pushing it out to 42 centimeters, which is 0.42 meters. Okay, so one more time, they said to go from here to here is 2 joules of work, 2 Newton meters. So I have to change everything in meters. They said 30 centimeters, that's a cm there if you can't see it, 30 centimeters, that's 0.3 meters. 42 centimeters is 0.42 meters. Okay, remember there's 100 centimeters in a meter. Now, when you're doing the formula, F equals Kx, okay? So from the previous problem, you basically integrate the force, okay? The force this time is Kx, we said. That's so-called Hooke's law. F is equal to Kx. But 0 is considered the natural position. So when you integrate, you're not going from 0.3 to 0.42, okay? You have to start with 0 being the natural position. So if this is 0, this is now 0.12. Okay, so the formula F equals Kx that I showed you before the break, okay, this is considered the 0. So we're going to be integrating from 0 to 0.12. Okay, so in the previous problem, right, we integrated the force. The force this time is Kx. What's interesting is we don't know what the K is, but we just leave it. We end up solving for K. So here you have to treat K as a constant. Okay, we have to find the K here. K might be 7, it might be 25 or whatever. Okay, and that's actually a key concept. I'll go ahead and give you a heads up that you need that concept when you're doing the quiz in a little while, where there's going to be a constant there, K. Okay, you pretend it's just another number like 7 or 3 or whatever. Okay, so the integral from 0 to 0.12 of Kx dx is equal to 2 joules, or we'll just say 2. All right, so here's the key thing. How do you integrate Kx dx? Okay, even though you see 2 letters here, K is a constant. So pretend it's like 3x or 10x or negative 50x. Okay, you leave this alone and you go x squared over 2. Right? So the integral of Kx dx is Kx squared over 2. Leave the K alone. Is that right? It's a constant. And again, you'll need that concept in a little while when I give you the quiz. From 0 to 0.12. Plug in 0, you get 0. I like that. So I just plug in 0.12. So I have K times 0.12 squared over 2 minus nothing. If you plug in 0, you get 0. And I set that equal to 2. Okay, the total amount of work was 2 joules. So I integrated the force function. This time the force is k times x. So k 0.12 squared over 2 is equal to 2. So solve for k. So I have k times this mess. To solve for k, just multiply by the reciprocal of this. The reciprocal of this is 2 over 0.12 squared. So there's k times 0.12 squared over 2 times 2 over 0.12 squared. I do that to both sides. If you can't quite see that, that's 2 over 0.12 squared. It's the reciprocal of this. So 2 times 2 over 0.12 squared, punch it in your calculator. It's 277.7 repeating. That's 2 times 2 over 0.12 squared. 277 and 7/9. Okay, so that's the k. So I found k to be 277.7 repeating. You guys know that bar over, right? It means it repeats. So my k is 277.7 repeating x. So now I know the force function is 277.7 repeating x. Now the second part of the problem, it's more complicated. Second part of the problem, I won't show you the book again, but it was there. Book's heavy. Okay, it says we're going from 35 to 40 centimeters. Okay, so it says how much work is there in moving the spring from 35 centimeters to 40 centimeters. All right, now the home position was 30 centimeters. To work the problem out, you always have to go in relation to the home position. So if home is 30 centimeters, if I move from 35 to 40, that's actually moving from 5 centimeters to 10 centimeters. Okay, so one more time, the home position is considered 0. That's how far away the spring is from the wall. Remember the picture that we had? It was something like this, right? So you have a spring. If you have a spring and you have a weight here, there's a natural position. If you let it go, it's going to want to be at a certain position. For this particular spring, it's 30 centimeters. Okay, now they're saying, suppose you're already at 35 centimeters and you want to move it to 40 centimeters. How much work is there? Okay, so if the home position is 30, then you're going from 5 to 10, right? 30 centimeters, 35 centimeters is 5 units away from home. 40 is 10 units away from home. So I'm going from 5 centimeters to 10 centimeters. Yeah, there's a lot of units that are mixed up here. But again, I have to change that to metric. Change it to meters. So what is 5 centimeters? 0.05 meters. What is 10 centimeters? 0.1 meters. Okay, so when I integrate, I'm going to go from 0.05 to 1 meters. So there's a lot of things going on in this problem, I know. I had to change it to meters because we agreed in the metric system, we're using meters, not centimeters. All right, so we're ready. We integrate the force function, just like the previous problem. Okay, you basically integrate the force. So the force is 277.7 repeating x dx, and you're going from 0.05 to 0.1. So that's the work needed to move the spring from 35 centimeters to 40 centimeters away from the wall, which means 5 centimeters to 10 centimeters away from home. So this is the way you set it up, from 0.05 to 0.1 of 277.7 repeating x dx. So leave alone the 277.7, x becomes x squared over 2 from 0.05 to 1, right? So I decided to put the 2 with this. So 277.7 repeating over 2, 0.1 squared minus 0.05 squared. Okay, so I'm going to show you that up at the top. Okay, so I'm going to write that divided by 2, 0.1 squared over 0.05 squared. And here we are. 277.7 repeating over 2, 0.1 squared minus 0.05 squared. Punch it in the machine, 1.04 joules. All right. That's part A. There was actually a part B. So let me go ahead and show you that part B real quickly. Let's see, where are we here? How far beyond its natural length will a force of 30 newtons keep the spring stretched? Okay, so the force is 30 newtons, and how far beyond its natural length? Okay, so force is 30 newtons, and I use the formula F equals kx. And again, you physics people know that formula, F equals kx. We now know K. K is 277.7 repeating. So I plug in 30 here. It's already the right units, newtons. K we now know is 277.7 repeating. And I just divide both sides by 277.7. Punch it in the machine, 0.108 meters. And that's correct in the metric system. But I'm going to change the answer to centimeters because everything in the original problem was centimeters. Okay, so even though technically this is correct, it's too weird if everything in the problem was centimeters, right? Centimeters, centimeters. Now we needed to change it to meters just to make the units work out. But a good general rule is you give back the answer in the units that it was given. So if everything in the original problem was centimeters, you should give it back in centimeters. So even though this is sort of correct, 0.108 meters, I present the final answer as 10.8 centimeters. And that's my final answer. Okay. All right, so then I was going to show you 21. Okay, an aquarium 2 meters long, 1 meter wide, and 1 meter deep is full of water. Find the work needed to pump half of the water out of the aquarium. Use the fact that the density of water is 1,000 kilograms per meters cubed. This is 1,000 kilograms per meter cubed. That's called the density of water. You can put that on your cheat sheet. Okay, now I'm going to change the problem a little to make it easier. Okay, it's full of water. Okay, now follow the logic that I'm giving. It asks to only pump out half the water. So if I pump out half the water, I'm going to pretend instead of being 1 meter deep, it's only half a meter deep, and I pump out all the water. I mean, that's essentially the same thing, right? Okay, so I'm going to change the problem. It's 2 meters long, 1 meter wide, and only half a meter high, and I'm pumping out all the water. That's the same thing as 1 meter deep, and I'm pumping out half the water, right? So they made us jump through one extra hoop. I don't know why, but there it is. Okay, so there's a lot of stuff going on here too. We have to take care of units, and I'll show you how to do that. So I'm going to show you this picture. Problem 21. Okay, here's my aquarium. It's 2 by 1 by a half. Okay, I didn't write the half. Oh yeah, I did write the half right here, 1/2 a meter. And I'm pumping all the water out the top, let's say, like that. Now, here's what's happening. Assuming we minimize the amount of work, force times distance, if I take this suction, let's say this thing is a suction sucking out the water, the most efficient way to suck out the water is if the suction is always at the top of the water level, right? So if you put the suction all the way at the bottom, it's kind of a waste because then you're forcing all the water molecules to go up the entire 1/2 a meter. But no, I mean, the water molecules at the top don't have to travel very far at all. And then as you keep going farther and farther down, right, you need to do more and more work just because it's a greater distance, right? See, the water molecules at the top, take them out, not that far. But the water molecules at the bottom have to do more work. I guess by analogy, pretend that there's a people. Okay, if you have people here, the people at the top don't have to travel that far, but the people at the bottom have to go much farther, right? Right. So what's different this time is the distance is not the same, right? The distance that the water molecules are traveling aren't the same. So what am I going to do? I made a little slice of water like so. So I drew myself this aquarium, right? And I have a little slice like that with a very thin delta X. So it's 2 meters by 1 meter by half a meter. And I have a very thin delta X. Okay, so it's almost like I have a sandwich of water. I know that sounds funny, but sandwich of water. Now, why do I slice like that? How come I don't slice this way, for instance? Okay, well, I claim that for this slice of water, if delta X is not very big, all the water molecules in here are traveling the same distance, right? They're all traveling the distance from here to here. So for this slice of water, it's like the gorilla problem. It's a constant force traveling a constant distance. Okay, now the top I call X equals 0. The bottom I call X equals a half. So how far do the top molecules go? They hardly go anywhere. It's practically 0. The water molecules at the bottom, though, have to travel the whole half a meter. Okay, so in general, this distance is X. So how far do the water molecules here have to travel? They're all traveling X. Okay? And yes, there's another slice at the top, another slice here, another slice here, another slice here. Okay, I'm not a good artist, as you can tell. I just normally do a typical slice. Chop, 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 chop it in a whole bunch of water sandwiches, so to speak. Okay, add them all up. You end up with a Riemann sum, which is an integral. Delta X approaches 0, n approaches infinity. You get an integral. So I have to figure out the force here. I already know the distance. The distance is X. Okay, what's the force on any of these slices? Okay, so I have to take the volume of this sandwich, the volume of this slice of water. Again, all the water molecules here are traveling the same units up, which is X. So it's length times width times height. It's 2 by 1 by delta X. The very tiny height is delta X. Okay, and you do a lot of this in your science classes. Any of you who've taken science, you may have seen units analysis, analysis of units, just get things to land it the right way. So what's my delta V, my change in volume? Length times width times height. So 2 meters by 1 meter by delta X meters. It's not half a meter. I'm only talking about that one slice. So I have meters times meters times meters, which is meters cubed. And that is the units of volume, is it not? So my little change in volume is 2 times 1, 2 delta X cubic meters. Okay, that's the volume. Now I have to translate that to a mass. Mass is measured in kilograms. Okay, so I have 2 delta X meters cubed. They told me that water is 1,000 kilograms per meters cubed. Okay, and you notice how I just get the units to cancel, right? That meters cubed cancels this meters cubed. So again, you have the volume of this sandwich of water times the density of water, 1,000 kilograms per meters cubed. And notice the meters cubes cancel out. That one cancels that one. So 2 times 1,000. So now my delta mass, delta M, is 2,000 delta X kilograms. 2,000 delta X kilograms. All right, that's the mass. Then I use F equals ma, force equals mass times acceleration. So I have the mass, which is in kilograms. I multiply by the acceleration due to gravity. Again, we're making the assumption that this is on Earth, not on the moon, not on Mars, not on the International Space Station or something like that. So I take that answer right here, a mass, 2,000 delta X kilograms, multiplied by the acceleration due to gravity on Earth, which is 9.8 meters per second squared. And then I have a kilogram meters per second squared. And some of you physics people know this, but if you never heard of it before, kilogram meters per second squared is a Newton. Okay, so going back way over here, a Newton is kilogram meters per second squared. Okay, mass times acceleration. So I have 2,000 delta x kilograms times 9.8 meters per second squared. So I have kilogram meters per second squared. That's a Newton. So I multiply 2,000 by 9.8, comes out to be 19,600 delta x newtons. So that's the weight or the force of this sandwich of water. That sandwich of water weighs this much if I were on Earth. Okay, 19,600 delta x newtons. Okay, it's a weight. So weight is a force. Okay, now if you're in the moon, this would not weigh as much, or on Mars. Okay, or if you're on the International Space Station, for instance, this would weigh 0. Right? It would be weightless, but you still have the same mass. Okay, and you physics people know this. You have the same mass whether you're on the moon or the Mars, or you have a different weight. And on Earth, you have a different weight. If you're on the International Space Station, your weight is 0, but you still have the same mass, right? Your mass is exactly the same thing. Okay, now I take that force, move it a distance. All these water molecules are moving the same distance, x. At the top, it's moving 0. At the bottom, it's moving half. So somewhere here, it's like 0.1 and 0.2, right? The water molecules have to travel farther the farther down you go. So I take that force times the distance is x meters. So I just multiply this force, 19,600 delta x newtons, times x meters. That gives me Newton meters. And Newton meters is a joule. So Nm is a joule. So if I multiply this all out, I have 19,600 x delta x. Okay, that was, of course, the hardest part, to line everything up the right way. So there it is. We've lined everything up the right way. That's what I integrate. Okay, so in the limit, delta x always becomes dx. So you're going to integrate the 19,600x, delta x becomes dx. What am I integrating from? 0 to half, because it's half a unit down. And there we go. So integral from 0 to half of 19,600x dx, and that's easy. The hard part, of course, is following all this stuff here. Okay, so 19,600, integral of x, x squared over 2. From 0 to a half, I like plugging in 0, you get 0. So I plug in a half, so 19,600, 1/2 squared divided by 2 minus nothing. Punch it in your calculator. 2450 joules is my answer. And there we go. Okay, folks, I know that's a lot to digest. Look it over. If you want to put parts of this or all of it on your cheat sheet, you may. But again, you're limited in what you can put. All right, so I was going to stop. I've done some of these. I'll do some more next Tuesday. So I think we're okay. I have next Tuesday and Thursday to just finish 6.4 and 6.5. It looks like I shouldn't have any problem with that. Okay, but for now, I'm going to stop and we'll go to our quiz. Okay, I'm still recording in case you don't want to write this down or take a picture. Then you can always check the video later. Okay, so it's quiz time. My recommendation is actually to get your cell phone out and take a picture so you don't have to write all of this stuff down. Okay, so get your cell phone out, quiz time, and I'll have to explain parts of it. And I don't even think I can get the whole thing on one. Yeah, I can't. So you're going to need 2 screenshots for this. So take a picture on your cell phone or do a screenshot as the case may be. So here's the top. Okay, the quiz is on the volume of a solid of revolution. We're only doing the disk method. Okay, So let me blab. I'll keep blabbing while you take a picture on your cell phone. You will derive some of the familiar formulas from geometry. Okay, and I'm even going to give you the answers, and you might not be able to see it. Sorry, but I'll give you the highlights. Okay, number one, the region bounded by the line y equals r over hx. All right, y equals r over hx. X equals r, and the x-axis is rotated about the x-axis. Okay, here's y equals r over hx. Okay, x equals r. You're going to spin this about the x-axis. Okay, if you take this triangle and spin it this way, disk method, can you see what you get? You get a cone whose radius is r and whose height is h. So you would derive the formula for the volume of a cone. Okay, here's the point h0. This is hr. Notice when you plug in h, you get r. The slope is rise over the run. So my delta y is r. My delta x is h. So the formula is y equals mx is y equals r over hx. Okay, so find the volume. I'm even giving you the answer. You could look it up on any geometry book. The volume is 1/3 pi r squared h. So if you can't see that, okay, what you're expecting is 1/3 pi r squared h. Okay, and a note, when you integrate, treat r and h as constants. Okay, and I mentioned that before. Okay, so the only variable is x. R and h, treat them as constants. Okay, everybody okay with this top half here? Okay, then number two, we sort of did a little bit already. Okay, the region bounded by the semicircle y equals square root of r squared minus x squared. Maybe you can read that. Y equals r squared minus x squared. Here's what it looks like. And it's bounded by the x-axis. Is rotated about the x-axis. So if I take this semicircle, by the way, if you do a little bit of algebra, that's x squared plus y squared equals r squared. Circle center of the origin with a radius of r. If you square both sides, right, you have y squared equals r squared minus x squared. Take a picture of this. Move the x squared over, you have x squared plus y squared equals r squared. But you don't really need to know that right now. Okay. If I take this semicircle and spin it about the x-axis, what do you get? You get a sphere. And we know the formula for the volume of a sphere. You can't read that. Four-thirds pi r cubed. So how do you like that? I'm already giving you the answers. Okay. Now you can't just write the answers and turn it in. I mean, you'll get a 0 for that. You have to show me the integration and so on. Okay. So y equals radical r squared minus x squared. Note, when integrating, treat r as a constant. Okay, so again, the only variable here is really x. R is treated as a constant. And there you go. And by the way, a hint, I think this is a very big hint. Instead of integrating from negative r to r, can you make the problem any easier? Right? And you can talk about it within your group. Okay, so there we go. So show you one more time if you need it. You have y equals r over hx. Both problems do the disk method. Here's the picture. Here's the answer. If you can't read it, 1/3 pi r squared h. And this one, y equals radical r squared minus x squared. Disk method for both of them. R is a constant. That should be your answer. Okay, so I will.
Mr. Hom?
Yeah, let me stop the share. Hang on, let me stop the share and turn off the recording.